So this example is going to be epic in the strongest sense of the word. So if you have some pump up music, you can play it, do some push-ups, get yourself stoked, because this is going to be awesome and a little bit intense. So here we go. So the challenge before us is to not just find a Laurent series expansion. We want to find all Laurent series expansions of this function around z equals 0. And it is really important that we specify around a certain point. As you start shifting your center, then everything changes. We're going to center ourselves at 0. These are some horribly lopsided circles, but you get the idea from my picture. So let's just think about it. I want to figure out, where is this function not analytic? This is a rational function, so I know that it fails to be analytic at 2 and at -1. And let's put those in pink. So here's a bad point at -1, and then here's a bad point at 2. And that's actually what's driving the circles, right? So you can see that, hey, on this region, this function is analytic. That's a closed disk, so we expect to find a Taylor series here. And then on this region, this blue region, this is an annulus. I'm analytic on that, so I'm going to find a Laurent series there, which is not going to be the same, by the way. And then this is another region, another annulus that I'm analytic on, all centered around 0. And so I'm actually going to have different Laurent series representations at each stage, right? On this disk, there is one Laurent series. On this purple annulus, there's one Laurent series. And on the green disk, there's one Laurent series. But they're different depending on the annulus. So let's write down just a couple of things as we dive into this. So first off, partial fraction decomposition. I'm not going to work that out for you. You guys did that in Calc 2 and great ideas, I'm sure. So you can do that if you've forgotten it or haven't seen it. Partial fraction decomposition. Check it out. Make sure you're comfortable doing that. I'm just going to write down that we're going to get 3 different Laurent expansions around 0. That way that's written down. Okay, and I'm thinking about my regions. I'm going to work my way inside out. So this is region 1, region 2, region 3. So we're going to start out with region 1. I'm going to need to carefully specify the restriction. So the region 1 is just modulus of z less than 1. So I've taken my function and I've broken it up like this. And let's please realize that the first one, 1 over 1 plus z, you should just know this. I guess I'll do it again. It's 1 over 1 minus z, and so you just do a geometric expansion. N equals 1 to infinity, minus 1 to the n, z to the n. And this is valid for modulus of z less than 1, which is exactly the disk we're on. So that's perfect. So I got that half done. And then for the other half, 1 over 2 minus z, I'm just going to do my classic algebra, pop the 2 out, and write this as 1/2 1 over 1 minus z over 2. And so, again, I can use a geometric expansion. I'm going to go ahead and pull that 2 in. I'm going to get z over 2 to the n. So z to the n over 2 to the n, but then I'm going to pull the downstairs 2 back inside. So it's going to be z to the n over 2 to the n plus 1. By the way, this is valid for modulus of z over 2 less than 1. And you need to pay attention to this, which is the same as modulus of z less than 2. So this particular expansion is valid for larger than the disk that I'm on. That's important because I might be able to use it on the next disk too, and I'll show you what I mean. Okay, so I don't have a single Laurent expansion. I have 2 different things. I need to combine these together. Notice that this is positive powers of z and this is positive powers of z, and the function that I want is this one plus this one. So I've got to add these 2 series, and since they're both positive powers of z, I can actually combine and get a single Taylor series here. And so here it is. I've actually already written it to save time. You've got minus 1. Whoops, I left off the minus 1 to the n. It's funny seeing mistakes minutes later. I can't go back and say anything about it, but oh well. So minus 1 to the n and then 1 over 2 to the n plus 1, all times z to the n. So pause the video, take a moment, and make sure that you're comfortable how we added those two series, and we got this. This is a Taylor series. It's also a Laurent series. Here the Laurent series is equal to the Taylor series, and we should add this is valid on our disk modulus of z less than 1. Okay, so now we're on to region 2. Region 2 is this purple disk in the middle, and so we should capture the equation, right? I'm saying that the modulus of z needs to be bigger than 1, but less than 2. And so, again, I'm going to look at my two pieces. Let's just copy those and write those down. So let's put that there. And I'm thinking about this first piece. So 1 over 1 plus z. I can rewrite this as 1 over z, 1 over 1 minus 1 over z. I'm just going to reinvent the wheel here. And this is exactly the sum n equals 1 to infinity of minus 1 to the n minus 1 over z to the n. I started mine at 1. You could start yours at 0 if you wanted to. It doesn't really matter. So I'm there. You can go back and recycle from the previous problem that we did if you want to. I just redirect it. I do need to check out that this is valid the way that I want it to be. But if you think about it, the modulus of 1 over z, that needs to be less than 1. That's the same as the modulus of z bigger than 1. So this particular expansion is valid as long as the modulus of z is bigger than 1, which we are. So I've got the first half. Here's a lot of negative powers of z. For the second one, I just want to go back and look at how we worked out this one. So we worked out 1 over 2 minus z before, and we got this series representation, and we said, hey, that's actually valid as long as the modulus of z is less than 2. Well, hey, that's where we are. Our annulus is inside the disk modulus of z less than 2. So I'm just going to copy this and not rewrite it all or rework it out. I just write it down. And so the point is, I actually can combine these two things into a true Laurent expansion. I've got the negative powers of z, and then I've got the positive powers of z, and you just add them together. So you just say, hey, this guy plus this guy, negative powers of z, positive powers of z, and then, by the way, this is valid on their overlapping region. So this one was actually valid for modulus of z bigger than 1. This one is valid for modulus of z less than 2. And when you put them together, you get exactly the region that we're on, right? The combination is valid on the intersection of those two things. And so that's the Laurent series expansion for region 2. Let's pound out region 3. So I want to work out when the modulus of z is bigger than 2. How do we find a Laurent series expansion for this guy? Well, let's do it. So again, I'm going to write down my formula just so you can see it. Let's realize that, hey, for this piece, last example on region 2, we found a Laurent expansion that was valid as long as modulus of z was bigger than 1. And if your modulus is bigger than 2, you're definitely bigger than 1. So we can recycle that. Let's just go up here. I'm going to copy this guy and just paste it. And this is common, by the way. This is part of the tricks of the trade here, looking to see when you can do this. So let's move the little period there. Okay. So I've got that one, so that's good. And then I have to focus on 1 over 2 minus z. That's going to change a little bit. Whoops, don't want the eraser. That's going to change things a little bit. So let's see if we can figure that one out. Well, let's think about what we're doing. So I'm assuming modulus of z is bigger than 2. That's the same as 2 over z being less than 1. So if I can get a 2 over z in my formula, it's less than 1. You could also manipulate this with z over 2 bigger than 1 and then reuse the geometric series that we found before. There are different ways, lots of ways to do this. I'm just going to flip it and say that's the same as 2 over the modulus of 2 over z less than 1. And so at this point, I need to play around now with my function and try and come up with that. So I can write this as minus 1 over z times 1 over 1 minus 2 over z. Do we agree with that? And then if I want to, actually I'm good to go at this point. I can say, okay, well, this is a geometric, I could find a geometric expansion for this because 2 over z is less than 1. So this is negative 1 over z times sum n equals 0 to infinity of, what are we going to get? We're going to get 2 over z to the n. Okay, well, that's the same thing as, the same thing as sum n equals 0 to infinity of 2 to the n. It's negative z to the n plus 1. And of course, this is valid for 2 bigger than modulus of z. And now let's think about it. So the first expansion that I found started at 1. This is my negative powers of z, starting them at 1. The second expansion I've got starts at 0. I actually worked this out a little differently before, so let me just adjust these. It doesn't really matter. We'll start it at 0. We're going to go 2 to the n, z to the n plus 1. There we go. And so we can, if we wanted, we could actually combine those together. If I wanted to combine these two series together, I have to reindex this one to 1 like I had. And let me do that now. I'm going to put it back. If you wanted to reindex this to 1, then you can do that. And this is 2 to the n minus 1, z to the n. And let me check. This is the same. Yeah, we're good to go. So if you want to reindex this one to 1, you can. And you can actually combine them because they're both negative powers of z, so it'd be nice to combine them. If one was negative, one positive, you don't combine those, but these are the same. They're all negative powers of z, and so you can actually write down the Laurent expansion. Wowee. So for each region, there's a different Laurent expansion, and we need to be able to find all of those. So I'll just end this very long video series with a couple of comments. Let me scroll down here. Just really one. You can integrate and you can differentiate Laurent series term by term as well. I don't think we stated that before. We said you could do it for Taylor series. You can do it for Laurent series. As long as you have a Laurent series that is convergent on an annulus, then you can integrate and differentiate as well. So here's some homework. I'll put these on the homework list online. I am recording this video on Thursday, April 9th, and I'm planning on making this homework due on, let me get to my calendar. I was thinking Friday, April 17th. This is a little longer video, so yeah, let's just do that. Friday, April 17th, this is due. All right.